Imagine a machine so unusual that it can crawl through deep mud, float across wetlands, and dig where ordinary excavators would sink in seconds. At first glance, it looks like a giant construction vehicle riding on floating steel platforms. But here's what nobody tells you. Every amphibious excavator represents thousands of hours of engineering, hundreds of tons of raw materials, and one of the most specialized manufacturing processes in heavy industry. And by the end of this journey, you'll see why building one is far more difficult than operating one. Most people never think about this, but some of the world's most important construction projects happen in places where the ground behaves more like soup than soil. Swamps, marshes, river deltas, and coastal wetlands can trap machines weighing tens of tons. Yet amphibious excavators work there every day, restoring waterways, preventing floods, and building critical infrastructure. The mystery is simple. How do engineers create a machine heavy enough to move mountains, yet light enough not to disappear into the mud? Microphone #3 narration. To answer that question, we need to travel backward through an extraordinary supply chain. We'll follow iron ore from giant mines, trace specialized steel through roaring mills, and step inside factories where sparks fly like fireworks. You'll see robotic welders, precision machining centers, and quality tests so brutal they would destroy ordinary equipment. And what happens during the final assembly stage surprised even experienced engineers. One microphone #narration. Everything begins with iron ore. Much of the high-strength steel used in amphibious excavators starts its journey in massive mines located in countries like Australia, Brazil, and Canada. Some open-pit mines stretch for kilometers and move hundreds of thousands of tons of rock every single day. Giant haul trucks carry or containing roughly 60 to 67% iron, and the scale feels almost impossible to comprehend. Imagine mountains being slowly transformed into machines. Microphone #2 narration. After extraction, the ore travels thousands of kilometers by rail and cargo ship to steel production facilities. There, blast furnaces operate at temperatures exceeding 1,500 degrees Celsius, or more than 2,700 degrees Fahrenheit. The air smells of hot metal and burning coke. Molten iron pours like glowing lava, lighting entire buildings with an orange glow. And this is only the beginning of the transformation. 3 Microphone #narration. The steel used for amphibious excavator pontoons must meet extremely demanding requirements. Engineers need strength, corrosion resistance, and durability all at the same time. Special alloying elements such as manganese, chromium, and nickel help create steel capable of surviving years in waterlogged environments. A single amphibious excavator may contain more than 25 tons of specially engineered steel, and every kilogram must perform flawlessly. 4 Microphone #narration. But steel is only part of the story. The hydraulic system relies on precision machined cylinders, pumps, valves, and hoses manufactured from specialized metals and synthetic materials. Rubber components often begin with natural rubber harvested in Southeast Asia and synthetic compounds produced in advanced chemical plants. Thousands of individual parts must travel across continents before they ever reach the factory floor. Think about this. A finished amphibious excavator may weigh more than 30 tons, yet its flotation system must distribute that weight carefully enough to travel across terrain that would swallow ordinary construction equipment. That requirement forces manufacturers to use huge quantities of precisely engineered steel while controlling every gram of unnecessary mass. It's a balancing act that begins long before the first weld ever appears. Of course, extracting and processing these raw materials comes with a cost. Mining operations consume enormous amounts of energy, while steel production remains one of the world's largest industrial sources of carbon emissions. Manufacturers now invest heavily in recycled steel, cleaner energy sources, and more efficient production methods. Yet even with these improvements, creating the raw materials for a single amphibious excavator remains a remarkable industrial undertaking. The moment the raw materials enter the factory, the pace changes completely. Huge steel plates weighing several tons move across the production floor on overhead cranes. Computer-controlled plasma cutters begin carving precise shapes that will eventually become the excavator's floating pontoons. Temperatures inside the cutting zone can exceed 20,000 degrees Celsius, or more than 36,000 degrees Fahrenheit, while cutting heads move at speeds approaching several meters per minute. The sound is a constant roar of electricity, hot metal, and flying sparks. Next comes bending and forming. Massive hydraulic press brakes apply hundreds of tons of force to shape thick steel plates into the curved structures needed for flotation pontoons. Some sections require multiple forming cycles lasting several minutes each. You can hear the deep groan of machinery as steel slowly changes shape. What looks effortless from a distance actually demands extraordinary precision because even a few millimeters of error can affect buoyancy. 9 Microphone hash narration. The formed sections now move to welding stations where the real structure begins to emerge. Robotic welding systems and highly skilled welders join hundreds of individual steel components together. Welding arcs reach temperatures near 6,500 degrees Celsius, or almost 11,700 degrees Fahrenheit. The air fills with the smell of heated metal, while blue-white flashes illuminate the factory like lightning storms. A single pontoon can require dozens of hours of continuous welding. But here's what nobody tells you. The pontoons are not simply hollow steel boxes. Inside, engineers install carefully designed compartments and reinforcement structures that improve strength and provide safety if damage occurs. Think of it as building a floating steel fortress hidden beneath the surface. Every internal section must withstand years of vibration, impacts, and exposure to water without failure. Once welding is complete, technicians inspect every critical seam using ultrasonic and magnetic particle testing. Sound waves travel through the steel searching for hidden defects invisible to the human eye. Even tiny cracks can trigger repairs before production continues. Most people never see this stage, yet it determines whether the machine survives years in some of the harshest environments on Earth. Meanwhile, another part of the factory builds the excavator's hydraulic heart. CNC machining centers cut steel components with tolerances measured in fractions of a millimeter. Rotating tools spin at thousands of RPM while coolant sprays across glowing metal surfaces. The machines never seem to stop. Day and night, they transform raw metal into precision cylinders, valves, and pump housings that control every movement of the finished excavator. Assembly begins when the completed pontoons meet the excavator body. Heavy-duty cranes carefully lower components weighing several tons into position. Workers guide the structures with incredible accuracy while hydraulic systems, engines, fuel tanks, and electrical networks come together piece by piece. The machine suddenly starts looking alive. What was once a collection of parts now resembles the amphibious giant it was designed to become. Then comes one of the most fascinating stages of the entire process. Technicians install specialized amphibious track systems designed to operate in both water and mud. Every track section must move smoothly while distributing weight across a large surface area. The completed system allows the excavator to travel across terrain that would trap conventional machines within seconds. What happens next surprised even experienced engineers. Before leaving the factory, every hydraulic circuit undergoes pressure testing. Hydraulic systems may operate at pressures exceeding 350 bar, or more than 5,000 psi. Engineers monitor sensors while pumps force hydraulic fluid through hoses, cylinders, and valves. The sound of rushing fluid echoes through the testing area. Any leak, vibration, or pressure drop immediately stops the process. Finally, the completed machine rolls toward a massive testing basin. For the first time, engineers watch as dozens of tons of steel enter the water. The excavator settles onto its pontoons exactly as calculations predicted. It floats. It moves. It performs exactly as intended. But building the machine was only half the challenge, because now it must prove that it can survive conditions far beyond anything found inside a factory. Now the steel has been refined. The hydraulic components have arrived. Thousands of precision parts sit waiting inside massive factories. But raw materials alone cannot create a machine capable of walking across a swamp. What happens next transforms ordinary metal into one of the most extraordinary excavators ever built. And this is where the real manufacturing story begins. The moment an amphibious excavator reaches the testing facility, an entirely new phase begins. Building the machine is impressive, but proving it can survive years in mud, water, heat, and constant vibration is something else entirely. Most people never think about this. A single hidden defect could cost hundreds of thousands of dollars once the machine reaches a remote wetland project. That's why engineers trust nothing and verify everything. One of the first systems to go to work is laser scanning technology. High-precision laser sensors sweep across the machine, creating a digital 3D model accurate to fractions of a millimeter. Thousands of measurements compare the finished structure against the original engineering design. Even slight distortions from welding or assembly become visible instantly. What looks perfect to the human eye can still fail a laser inspection. Next, AI-powered vision systems examine thousands of welds. High-resolution cameras capture images from every angle while machine learning software searches for tiny imperfections. The system can detect flaws smaller than a millimeter and compare them against thousands of approved weld profiles. In some factories, automated inspection systems review more welds in a few hours than a human inspector could examine in several days. But here's where it gets truly extraordinary. Despite all this technology, some inspections still depend on human expertise. Veteran weld inspectors often spend decades learning how to recognize subtle signs of stress, distortion, and workmanship issues. Sometimes a trained specialist notices a problem before any computer system flags it. In a world full of automation, human judgment still protects some of the most important decisions. Now the machine faces structural stress testing. Hydraulic actuators apply enormous forces to the boom, arm, and chassis, simulating years of real-world operation in just days. Sensors measure deformation down to tiny fractions of a millimeter. Steel groans under load. Hydraulic pumps hum continuously. Engineers watch live data streams while computers compare results against design limits. What happens next surprised even experienced engineers. Manufacturers also conduct flotation and stability tests under carefully controlled conditions. Engineers intentionally shift weight, extend booms, and simulate uneven ground conditions to verify balance and buoyancy. The machine must remain stable while handling heavy loads in waterlogged environments. A few degrees of unexpected tilt could create serious operational risks. Every movement gets recorded, measured, and analyzed. Hydraulic reliability testing pushes components to their limits. Pumps operate for hundreds of continuous hours while fluid temperatures climb above 80 degrees Celsius, or 176 degrees Fahrenheit. Pressure cycles repeatedly rise and fall thousands of times. The goal is simple: find weaknesses inside the factory before customers discover them in the field. Every successful test represents future reliability. Corrosion resistance receives special attention because amphibious excavators spend years surrounded by water, mud, and harsh environmental conditions. Protective coatings undergo accelerated weather testing inside specialized chambers. Salt spray, humidity, temperature changes, and chemical exposure simulate years of environmental damage. What takes nature a decade to accomplish can be reproduced in weeks inside these facilities. The numbers behind quality control are astonishing. Some manufacturers target dimensional tolerances below 1 mm for critical assemblies. Rejection rates for major structural defects often remain well below 1%. International standards such as ISO quality certifications guide every stage of production. By the time an amphibious excavator reaches a customer, it has survived inspections, measurements, and tests that most industrial products never experience. And yet one final challenge remains. The machine has proven its strength. It has proven its precision. It has even proven its ability to float. But before it can begin work in wetlands, rivers, and coastal projects around the world, it must join an industry undergoing rapid technological transformation. The future of amphibious excavators may look very different from anything we've seen so far. Today, amphibious excavators operate on nearly every continent, from the river systems of Southeast Asia to the coastal restoration projects of North America and Europe. While they represent only a small fraction of the global excavator market, their impact reaches far beyond their production numbers. These machines help maintain waterways, protect communities from flooding, restore damaged ecosystems, and support critical infrastructure projects. Most people never see them, yet millions of lives benefit from their work every year. The global excavator industry produces hundreds of thousands of machines annually, generating a market worth tens of billions of dollars. Amphibious excavators account for only a specialized portion of that industry, making them some of the most unique machines on the planet. Think about this. While ordinary excavators dominate construction sites, amphibious excavators operate where almost no other heavy equipment can survive. Their rarity is exactly what makes them so valuable. China leads global excavator production, followed by countries such as Japan, South Korea, the United States, and Germany. Together, these manufacturing powerhouses produce the majority of the world's advanced construction equipment. Behind every machine stand engineers, welders, machinists, software specialists, logistics experts, and quality inspectors. Worldwide, hundreds of thousands of skilled workers contribute directly or indirectly to heavy equipment manufacturing. Now let's travel back in time. 50 years ago, wetland operations often relied on improvised solutions, temporary platforms, and equipment never designed for soft terrain. Engineers quickly discovered the limitations. Machines became trapped. Projects slowed. Costs increased dramatically. That challenge sparked the development of increasingly sophisticated amphibious excavation systems that transformed entire industries. And this is where it gets truly extraordinary. Modern amphibious excavators use advanced hydraulics, satellite positioning systems, digital monitoring technology, and sophisticated flotation designs that early engineers could barely imagine. What once required constant improvisation now depends on precision engineering and real-time data. The transformation has been nothing short of remarkable. Did you know that some amphibious excavators can work in water depths that would completely disable conventional construction equipment? Did you know that their flotation systems distribute weight so effectively that they can travel across terrain resembling liquid mud? And did you know that a single machine may operate in conditions that change dramatically from 1 hour to the next? These are challenges few other machines ever face. Looking ahead, the next decade could bring even greater changes. Manufacturers are developing hybrid power systems, smarter automation, advanced remote control capabilities, and AI-assisted operating technologies. Future machines may reduce fuel consumption, improve precision, and enhance safety while working in some of the world's most challenging environments. What happens next may redefine how humanity manages waterways and fragile ecosystems. But after all the numbers, technology, and engineering, the most important story remains surprisingly simple. Somewhere in a distant mine, raw materials began a journey. They traveled through steel mills, machine shops, assembly plants, testing facilities, and inspection centers. Piece by piece, engineers transformed ordinary materials into a machine capable of work. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you